Hello, Geo212 class. Welcome to week 10. This will actually be chapter 9 in the textbook that I'll be bringing highlights to you. This is a very lengthy chapter, so I've decided to split it up into two separate lectures, part 1 and part 2. The first lecture will be in regards to planetary circulation. This is an extremely important aspect of both climatology and meteorology. And the second half is going to be taking a look at some jet stream, monsoon, also very important. So a lot of material in this chapter. So let's get started with planetary circulation. Okay, the first thing you're looking at here is planet Earth idealized without land masses. Land masses really mess things up theoretically. We'll learn about that a little bit. But if we just didn't have any land masses, what would happen? What kind of circulation would we see on the Earth? The first thing that's really important to understand is we have 4 specific zones on this planet. Okay, let's start down here with, it says L, and you'll see a dotted line across here. This is called the Intertropical Convergence Zone. We refer to it as the ITCZ. It's low pressure because it's the warmest surface of the planet. Warm surface, land, ocean will cause air to rise above it. Okay, convection. We've learned about this before. So we get this continual zone of rising air. If you're lifting the air off the surface, you're creating low pressure at the surface. That's why we see all these L's, and that's why the Intertropical Convergence Zone is a zone of low pressure. Now, because air is rising above the ITCZ, we're going to get a lot of cloud. We're going to get a lot of condensation and rain. So it's really, if you look at, if any given time you looked at a satellite image of Earth, you would see really a continuous belt of cloud along the Intertropical Convergence Zone. Now, we call it the Intertropical Convergence Zone because low pressure, look at this, it's pulling air in from the north and it's pulling air in from the south. And this air is converging at the surface. Low pressure is pulling it in and the air is converging from the north and the south. So this converging air then also gets into the rising convective air. So you're getting a lot of air moving in and rising, causing condensation, rain, and showers. So we call this zone 1, if you like, Intertropical Convergence Zone, a zone that's cloudy, a lot of thunderstorms, all right? Now, what happens if we look along the side here, air is rising at the Intertropical Convergence Zone. So it rises, and some of that air, as you can see, curves to the north in the northern hemisphere and starts descending at around 30 degrees north latitude. Now, descending air has the opposite effect of ascending air. Descending air is going to compress the atmosphere. It's going to warm it up and dry it up. So then this zone at around 30 degrees, and it's really approximate, around 30 degrees, a zone of air moving down from the upper atmosphere, creating high pressure. So in other words, atmosphere descending is pushing down on the atmosphere, creates high pressure here at around 30 degrees. Now, this zone then is compressed air, it's dry air. This zone is going to be the opposite of the ITCZ. It's going to be pretty cloud-free most of the time. Not always, but generally it's going to be an area dominated by high pressure, which is fair weather, dry weather. Okay, call that zone 2. We call this zone subtropical high pressure. Okay, now, as that air descends over here, it also then can start moving further north along the surface. Eventually, that's going to encounter this very cold polar air that sits over the Arctic. Cold polar air, it's dense. So this relatively warm air that's moving up on the surface, when it encounters that cold, dense air, it's going to be forced to rise, it's going to be forced to lift. We're lifting the air, a lifting mechanism. Anytime we lift air, we cool it, condense it, form clouds, precipitation. So in this area of rising air then, we'll call it the third zone. We call this the zone of subpolar low pressure because the air, relatively warm air forced to rise up above the cold, dense air of the Arctic. So zone 3 then, subpolar low pressure. Zone 4 I've already touched on. It's simply polar high pressure. Cold, dense air pushing down at the surface in these polar regions, creating high pressure, dry. Okay? So if we look at this particular depiction, then after I've explained some of this, if you look at the depiction here, low pressure around equatorial regions. This is the intertropical convergence zone. We move up to high pressure, subtropical high pressure, and then we move up to subpolar low pressure, and finally at the North Pole we have polar high pressure. Okay. Now, when we throw the land onto this idealized thing we just looked at, things get a little more complicated, but it still follows the same pattern. If we take a look at this, let's go down here actually and look at July. This is the average July settings for global circulation. So they're not really showing much around the intertropical convergence zone, but it would be right along the zero latitude, approximately there. But what's important for North America, really important for us, up here, subtropical high here, subtropical high here. These are very important to the climate of the United States. The high pressure out here over the Pacific Ocean is referred to as the Pacific High. Clockwise circulation, you can see it's going to be clockwise circulation, and that's going to drive the ocean surface currents the same direction the wind is going. So one thing to understand here, these surface features, like in this case the Pacific high pressure system, as it rotates clockwise around it, it's going to drive our ocean surface currents the same direction. Therefore, we get ocean currents moving from the north, from British Columbia and Alaska, down along the coast of Washington, Oregon, California, and down into Baja California. Cold water. This produces cold surface water year-round off the west coast of North America. That's the Pacific High. We come over here into the Atlantic, we've got the Bermuda High. The Bermuda High, again, clockwise circulation, but really opposite effect of the Pacific High in terms of ocean temperature. That clockwise circulation is bringing extremely warm surface water up from the Caribbean and running it up along the east coast of the United States. As a matter of fact, it continues on over into Europe, Scandinavia, and even into Russia, creating very warm water up in that area. So this warm water then has a different effect on the climate we'll talk about a little later. Okay, so that's your July average locations. You don't see a lot of low pressure in July. That would be what we call, that's one of the subpolar lows. That's what we call the Icelandic low. But let's move up into January, and we can see these, we'll start from the north. The subpolar lows develop quite a bit more in the wintertime in North America. There's your Icelandic low, counterclockwise circulation, creating a lot of storms that can move off over into Europe. Occasionally, they'll even move into North America, but not usually. They'll usually follow the westerlies and go into Asia. This is the big one, though. This is called the Aleutian Low. It's named after the Aleutian Islands, that long volcanic chain of islands off of Alaska. And this sets itself up pretty much in the Gulf of Alaska in the wintertime and produces a lot of storms. As a matter of fact, those of you who have been following the weather just over the weekend, late last week, couple of these extremely powerful subpolar low pressure systems that had actually gotten together with typhoons hit the northwestern part of the United States and southern British Columbia, creating very high winds and very heavy rains. Did a lot of damage, actually. So that was thanks in part to this Aleutian low pressure system here. All right, let's move on. We'll explain some of this more. Again, just another depiction of what the winds would be doing in this pattern. You can see that here along the ITCZ, just north of the equator, we're going to have easterly winds blowing. That's going to become important later on. We start talking about El Nino and La Nina, second half of the chapter here. This area also is referred to as the trade winds, these easterly winds that blow just north of the equator. Okay, as we move to the north of that, you can see here's our subtropical anticyclones or high pressure systems blowing clockwise, and these produce the westerly winds in the mid latitudes where we live. Look at that circulation pattern at 30 degrees. It's going to turn those winds toward the west at our latitudes, 35 to 45 or so degrees north latitude. So it's a subtropical anticyclone or high pressure system. Pacific High and the Bermuda High, they're going to produce the westerly winds, the dominant westerly winds where we live here in North America. Now, as we get north of the polar front, you can see you're going to have high pressure there. It's going to be producing what we call the polar easterlies, all right? But there is going to be the frontal boundary, and it's along this frontal boundary we're going to see these subpolar low pressure systems develop. So again, just to keep in mind those 4 zones, we start here, the first zone, intertropical convergence zone, a cloudy zone, a lot of precipitation. Then we move up here into the subtropical anticyclone or high pressure area. That's going to be relatively dry weather. Then that's the second zone. The third zone is going to be along this polar front where warm air is going to ascend and lift over that cold polar air and create low pressure systems, subpolar low. And then finally the fourth zone up here in polar high pressure. Same thing happens in the southern hemisphere, but we'll just talk about the northern hemisphere since that's where we live. Now, I've written down a lot of material you can go ahead and read on your own. This is just putting in writing most of what I've just been talking about, subtropical anticyclones or high pressure systems. Again, here is some more written material you can take a look at, but I've already spoken to this. Same with this here. All right, now here's something else that we could take a look at. This is a cross-sectional look at the intertropical convergence zone, maybe get a little better idea of what's going on in 3-dimension here. Remember, down in these equatorial regions, the ground is at its hottest, so it's causing lift, convective lift, creating a lot of thunderstorms, cumulonimbus clouds. But as that air lifts, look what it's going to do. Let's go over here to the northern hemisphere. It's going to curl back at high altitude and then descend at around 30 degrees north. Remember, descending air, opposite of rising or lifted air, it's going to be dry and warm. So at this zone, this is the subtropical high pressure zone. So first zone, ITCZ, rising air, air curls back, descends at 30 degrees north, creating dry, compressed air. Okay. Now, this rotation of air, and this air as it descends at 30 degrees can move both north and come back down toward the equator. As it rotates around like this, it's referred to as the Hadley cell. Okay, it was named after a meteorologist by the name of Hadley. Another look, a cross-sectional look, might help you out sort of understanding how this circulation works as well. This particular slide is talking about where is the tropopause. The tropopause, recall, is the boundary or the very top of the troposphere, the boundary between the troposphere and the stratosphere. So we can see that down here in these lower equatorial regions, the tropopause is at the highest altitude you're going to find it. But then as we come further up into our latitudes, where a lot of this warm air is ascending over the polar front and creating subpolar low pressure systems, we see that the tropopause is coming lower in elevation. So the troposphere is not as thick or as high into the atmosphere. And finally, when we get up into these cold polar regions, the tropopause is even lower. Denser air, colder air, so these atmospheric molecules will be closer together, more packed together. So the top of the troposphere then is simply going to be lower. Warmer air down here by the equator causes the atmospheric molecules to be further apart, therefore giving us a thicker troposphere, and then thinner here, or not as high anyway, because the air is colder and denser. Okay, winds aloft, if we take a look at, we've been sort of looking at a cross-sectional view of winds aloft. What we can see is, if we're looking down, this would be the subtropical high area here, and this is the subpolar low area here. If we're looking at winds aloft, when we see this kind of thing happening, when we see the wind in the northern hemisphere do this dip like this in the upper air, we call that a trough. It's an area of low pressure. We'll be looking at more of that later on in the course when we take a closer look at upper air patterns. Then when we see the air going up more in this counterclockwise circulation like this, high pressure, we refer to it as a ridge. Okay. Also, another term here that we introduce in upper air, when we get the upper air pattern flowing fairly straight across from west to east. This is referred to as zonal flow, where it pretty much goes west to east. But when we get these large excursions, Sam, watch the arrow here, where this could come way down and then come way back up, that's referred to as meridional flow. So just keep that in mind for later on when we start talking about upper air. Okay, this is extremely important now. This is probably one of the most important aspects here. Seasonal shifts in these four zones I've been talking about. You know that the sun, because of the 47 degree, or rather the 23.5 degree shift on its axis, this causes the sun to be higher and lower in the atmosphere over the course of a year. So for example, in the northern hemisphere, around June 21st, the sun is at its highest, okay? So at that time, it causes all these four zones to shift to the north, okay? So the ITCZ shifts further to the north. The subtropical high pressure system area shifts further to the north. Subpolar shifts further north, and so on and so forth. And just the opposite happens in the winter. These four zones start shifting further to the south. And why that might be really important for Arizona, for example, is if you take a look at the climate in northern Arizona, what you're going to find is we get a seasonal precipitation maximum in the winter. Why is that? Well, it's because the subpolar low pressure zone is shifted to the south because the sun is far to the south. It's kind of basically pulling all these zones to the south. So we get interaction with a lot more subpolar low pressure systems, and we get, on average, I would say Prescott at any rate, receives about anywhere from about 55 to 65% of its precipitation in the winter. The rest, of course, coming during the summer monsoon season. All right. So seasonal shifts, these zones shift back and forth. And here is a map just depicting, for example, where the intertropical convergence zone is going to be in January based on July. Now look how much further south in January the ITCZ is compared to where it is in the summertime. Now this is really important for places, for example, in Africa, because remember, the ITCZ represents a narrow band of area where it's pretty wet. And so particularly over here in East Africa, which is fairly dry, you can see that this area up here, probably northern Tanzania, Somalia, places like that, are getting their, Ethiopia, are getting their seasonal rainfall in July. So when we talk about the rainy season in East Africa, you know, this part of Africa here in July, it's rainy. It's going to be dry down here. But as the sun shifts to the south during our winter, during southern hemisphere summer, it pulls that ITCZ way down to the south here. And so it's drier, it's a dry season up here and a wet season down here. So the intertropical convergence zone, it can explain why certain locations on the planet have a wet season and a dry season. All right, as I mentioned earlier, ocean surface currents are driven by the surface wind of surface systems, high pressure systems for the most part, okay? And we call them gyres. Gyres are these large scale circulation patterns in the ocean, okay? And they do appear in the major ocean basins. And let's put a map up here so we can understand it. So one of the great Pacific gyres rather, up here, look at this clockwise circulation in the Pacific Ocean. And that's a result of the Pacific high pressure system causing clockwise circulation. It drives this Pacific current clockwise like this. It's kind of funny. One of the ways this has been verified is that there's been a couple of cases where ships have gone down and their cargo has been cut loose. And in one case, there were Nike tennis shoes, running shoes, whatever you want to call them, was on a ship out about in this area here. It went down and it released tens of thousands of these floating shoes. And these shoes then carried across in the North Pacific Current, and thousands washed up along the shoreline all the way from Vancouver Island down along in the California coast. And a lot of them ended up returning back to Japan and then kept recirculating. So it's been interesting that we've been able to verify this North Pacific Current and the North Equatorial Current from ships that have released some of their cargo. So that's an important current for us. You can see that it drives this very cold water down. It's called the California Current along the west coast of the United States. And it produces very cold water, which does not allow much evaporation. Therefore, that's why the entire West Coast, in the summer at any rate, is pretty dry. We're not getting much evaporation off the ocean. Therefore, there's very little humidity in the atmosphere. We go over here to the North Atlantic, however, we have the Bermuda High that's circulating clockwise, and it's driving, look at it's driving this current clockwise, in particular the Gulf Stream current. This is extremely warm water carried all the way up the East Coast and into the Gulf of Mexico. And the air circulation around the Bermuda High moves or advects this moist air into the eastern half, or at least the eastern third of the United States. And that's why it's so humid in this area in the summertime, because of this advecting, very humid air off of extremely warm surface water in the Atlantic Ocean. Okay, quite a bit different from out here, as I said, where cold water is driven down the West Coast, which produces very dry air. So just an overview then, and just remember that these surface features, high pressure systems and also low pressure systems, do create sea surface currents. Okay, I'm going to end it here for part 1, as I said, and then I'll put part 2 in for monsoonal circulation. So pick up, starting here, monsoon circulation, when we do part 2.